Hey everyone, bit of a different video this time around. I had the opportunity this past week to present my master's research at a conference, and I thought it would be fun to share it here with you guys. So I've linked to my full research dissertation in the description, and if you have any questions, please leave them in the comments down below. We'll be back on track with a couple of more expected videos. I have a lot of projects in the pipeline. They're just taking a little longer to complete than I had originally anticipated. So stay tuned, and I'll catch you guys in the next one.
Hi everyone, my name is Keegan Crankshaw, and in this presentation I'm going to be sharing with you my research and findings into media clock recovery over Ethernet using IEEE 1722 on an FPGA. In this presentation I will share with you some background and context, the research focus, my methodology, design and findings, as well as my conclusions and some ideas for future work. Vehicles are becoming increasingly more complex, feature-rich machines. Things such as Bluetooth infotainment, cameras to assist with parking, these used to be luxuries but are now commonplace. And modern vehicles are becoming increasingly impressive to the point that some of them even drive themselves. This complexity, however, does come at a cost. Current intra-vehicle networks used to transport information, such as CAN, LIN, and MOST, are essentially a limiting factor as they require additional complex cabling for each new node, and there are significant bandwidth limits. This leads to heavy, complex, and expensive wire harnesses. In order to alleviate these issues, Ethernet is being investigated. Ethernet is a good alternative as it is high bandwidth, cheap, and a well-established standard. However, there is one concern with Ethernet, and that is the focus of this research. The reality is that vehicles rely on time-sensitive information. For example, sensor data in driverless cars. A move to Ethernet will naturally need to facilitate the transfer of time-sensitive information. Verifying time-sensitive information can be difficult when using sensor data, so a simpler application of real-time audio was chosen. And this is where IEEE 1722 comes in. IEEE 1722, which is the standard for a transport protocol for time-sensitive applications in bridged local area networks, exists at layer 2, meaning we can implement it on almost any network. It has an array of definitions to ensure determinism and throughput. There are also additional 802 standards, which make Ethernet deterministic, but these were not considered in this research, and the scope was solely placed on IEEE 1722 and what it has to offer. Ultimately, the focus of the research was to implement a version of the IEEE 1722 standard on an FPGA that can correct two asynchronous media clocks to within a 5% phase difference. We also intended to investigate factors which could allow for a successful implementation, and which factors affected implementation. And finally, we aimed to provide a framework for further development and experimentation. In this research, a Cyclone 5 FPGA was used to implement a 1722 talker and listener. Primary software tools used were the Quartus suite, Wireshark, and Python tools for simulation. Various design methodologies were used to ensure timeous completion of deliverables, and testing occurred with hardware in the loop, as well as Python simulations of the proposed correction algorithms. This is an image showing the testing setup. The FPGA consists of two logically independent components, a listener, which receives IEEE 1722 packets, and a talker, which packages and transmits them. An additional button was used to trigger resets on the FPGA. An oscilloscope captured the output media clocks of both the listener and talker so that their phases could be compared, and a router was inserted in order to be able to capture the Ethernet data from the FPGA. These two images show the primary system design split between the talker on the left and the listener on the right. The talker has a fairly simple task: package timestamps in the CRC format and transmit them over Ethernet. It does this using a dual clock FIFO to capture and transmit timestamps between the two clock domains in the design. The listener's task, however, is much more complex. It needs to receive these CRC packets, extract timestamp information, compare the captured timestamps to its own internal timestamps, and then correct its clock in order to align its phase. The data flow works essentially as follows. Data comes in through the Ethernet component and is passed through to the AVTPDU processor. This extracts timestamps from the Ethernet frames and places them in a dual clock FIFO. timestamps are then read by the CS2000 clock generator, which is aware of the shared timing reference between talker and listener. This CS2000 clock generator also pulls timestamps from its local media clock. It then compares these two timestamps and uses the offset to adjust the control wave passed to the CS2000 clock generator. This clock generator is used to generate the media clock of the listener. The feedback loop is now closed, and the listener is able to correct its own local media clock based upon timestamps received from the talker. This plot shows the phase difference between the talker and the listener media clocks. The data was captured off a Keysight oscilloscope using the BenchView software. The blue trace shows what happens without any feedback, and it is as expected, the two clocks drift. Once the loop is closed, shown in red, the phase relationship is much smaller and much more consistent. The clock correction algorithm, along with a simple averaging filter applied to it, ensures that the two clocks remain within roughly 6 degrees of phase, well within the 5% requirement stipulated by the IEEE 1722 standard. From this, we can conclude that the primary objective of synchronizing two media clocks over Ethernet was successful. The system implemented was able to correct the listener clock to well within the IEEE 1722 requirements. However, some sources of jitter, such as variations in temperature, were found, but these were not investigated further as they were out of scope. As such, future suggested work is to further investigate these sources of jitter, perhaps implement a more robust filter for corrections to the listener clock in order to reduce this jitter, implement a holdover system to maintain the last known best phase correction in the event of network loss, and also include additional aspects from the IEEE specification which were deemed inapplicable to this test case. I would like to acknowledge the following two groups for their assistance in supporting this research and publication. The following are some applicable references from this presentation.
And that's it. Thanks for watching, guys. If you have any questions, as I said, please leave them in the comments down below, and I'll check you guys in the next one.